Welcome back. So let's continue our foray into general relativity. We want to understand what does it mean for space-time to be curved. But to do that, we first need to understand what it means for anything to be curved. And to do that the mathematical way, we need an object called a metric. So what is a metric? Well, let's just start in the regular xy plane that we know from geometry. So this is just two dimensions. Here's x, and here's y. And suppose that we have 2 points in this plane. So one's down here, and one's up here. And these are separated by certain distances along our coordinate axes. So here's a dx, and here's a dy. And we're interested in the length of the shortest path between these 2 points, which is, we'll call ds. So this is pretty easy. We know from our friend Pythagoras that ds squared equals dx squared plus dy squared. So that's pretty simple, and it holds, for any 2 points that are anywhere in the plane if these are the separations between them. But let's try to write this in a slightly more suggestive way. So I'm going to peel out these dx's. So I'm going to make a little vector here, which is like a 2x1 matrix. So here's dx, dy. And I'll peel off this matrix, which looks like 1, 0, 0, 1. And then I'll put another 2x1 column vector here. So if you remember how to multiply matrices, so remember you go across a row and down a column and kind of multiply and add together. So when you do this, you'll get a dx plus 0 in the top and a 0 plus dy in the bottom. And then when you do the same thing with this one, you get a dx times a dx, which gives dx squared, plus a dy times dy, which gives dy squared. So this is just the same thing, but it's being written in a different way. Now once we've done this, once we've kind of written the distance between 2 points as this kind of vector dot matrix dot vector, this object here is called the metric. So this will be the main object we want to study. So this is the metric. And notice that for the Euclidean 2D plane, the metric is constant. It doesn't depend on x or y. No matter where you are in the plane, the distance between 2 nearby points is going to be given by the same relationship between them. They just square the distances between the 2 in x and y. So not only is it constant everywhere in the plane, but it's diagonal. So it only depends on dx squared and dy squared separately, and maybe not on the product dx, dy, or anything weird like that. So this is an example where there is no curvature. Everything is very flat. So to contrast that, let's think of a slightly more complicated example. So we're going to look at the surface of a sphere. So you can think of this as the surface of the Earth, for example. So we have now more axes. So I'll draw them a little bigger to make it pretty clear. So these will be x, y, and z. And we have maybe blue again to imagine this is the surface of the Earth. So we have some circle, which I haven't drawn especially well, so maybe I'll just draw kind of like a hemisphere of it. So it's a little slightly better. So we have some circle like this, and we want to put a point on the circle in spherical coordinates. So here's a point on the circle, and we have spherical coordinates, so if the radius of the circle is r, and then we measure this angle between that point and the z-axis and call that theta. And then we have this other angle where we project this down on the xy plane. And then the angle between that guy and the x-axis is phi. So now what if we have another point that's nearby on the sphere, like down here? So this is a point that's nearby on the sphere. And then to get from the first point to that second point, let's use a slightly different color. So we first need to kind of go down like this from the original theta value to a new theta value down here. So maybe this guy, we just have a little dotted line here. So we need to go from the old theta, which maybe I should just illustrate that that's the angle between this guy and the z-axis. So we have to go from that old theta to a new theta. So now we have to go by a d theta that's a little different. And now once we're at that new theta, we need to rotate over here to a new phi value. So if this guy project down like this, then this amount we have to change in phi is d phi. And we're interested now in the total distance between the two. So this was like our ds like before. So this diagram's getting a little complicated, but let's see if we can just figure out what are the lengths of these two components of our path. So this component here, this component is a circular arc. It's the arc of a circle. If you think of a circular slice of this sphere, the circle has radius r and it subtends angle d theta. So the length of this side, maybe I can just kind of pull out a little bit. So this side over here has length r d theta. And this one over here is also a circular slice, so you can think of that as a kind of slice, taking a slice parallel to the xy plane, a slice like this. And that circular slice has a radius of r sine theta, right? Because r sine theta gives the kind of radius. Maybe I should do it a little better. So if here's if I draw it, this diagram will get more complicated. But so this guy is kind of, there's a radius here of r sine theta. Just try to draw small. So there's a radius r, it's really r sine of theta plus d theta, but if d theta is small, we can ignore it. So the radius of the circle is r sine theta, and it subtends an angle d phi along that circle. So the length of this guy is r sine theta d phi. And now if we consider an infinitesimal separation, so that's why I ignored that theta plus d theta, now we're going to imagine that these points are very, very, very close together. And that's the only case that we're going to care about. When we write a metric, we really only care about the distance between infinitesimally close points. So if these points are very, very close together, so that sine theta plus d theta is roughly just sine theta, then this kind of gets very close to a triangle. Gets very close to a triangle, and we can approximately, as in the limit as these small angles go to 0, we can approximately use the Pythagorean theorem again. And that would give us ds squared is this leg of the triangle squared, so r squared d theta squared, and this leg of the triangle squared plus r squared sine squared theta d phi squared. And if we write that in the metric formalism again, so this is so d theta and d phi, and then there's our metric, so this guy has an r squared and a 0, 0, r squared sine squared theta. And then over here we have again d theta and d phi. So now our metric, notice it's no longer this 1 and 1 on the diagonal that we saw before, but now it depends on what radius you're at. So if you imagine being on the surface of the sphere and then moving out to a different radius, like a different radius like capital R instead of little r, now the distance between points changes. In order to go from a point to a nearby point, changes by a little theta, for example. Before you needed to go only this r squared d theta squared, little r squared, and then if you move out to a bigger r, you need to go a larger distance. You need to go big r squared d theta squared in order to achieve the same change in theta. And likewise, it depends on where you are on the sphere. So if you're on the surface of the Earth and you want to change your angle phi by a little bit, the distance you have to go depends on where you are. If you're at the North Pole, you don't have to do you don't have to move at all to change your phi. You can just spin in place and then your angle phi changes and you haven't actually moved by any distance. But if you're all the way down at the equator and you want to move from, say, this point here over to this point here, so from the x-axis to the y-axis, you have to go by a lot. To change phi by 90 degrees, you have to go the radius of the Earth times that, times 90 divided by 360, so like roughly, if I can do arithmetic, you have to go 1/4 of the way around 2 pi r, so that's a quarter of the entire circumference of the Earth. So that's like pi over 2r. So this depends on where you are, and this is a hallmark of curvature. We'll see that this idea of a metric that depends on where you are in space is associated with a curved surface. So this matches our intuition that the surface of the Earth is indeed curved, and we'll see how to formalize this and write it down in a way that we can do calculus with it and use this to describe the motion of physical bodies in the next video.